Hi. Today we are presenting our recent findings on estimating human muscular fatigue in dynamic collaborative robotic tasks with learning-based models. Assessing human muscle fatigue is critical for optimizing performance in physical human-robot interaction tasks and mitigating safety risks for the human operator. Such tasks are also known as pHRI tasks. This study presents a data-driven framework for estimating muscle fatigue in dynamic pHRI tasks using surface electromyography sensors attached to the human arm. To estimate fatigue level during cyclic pHRI tasks, subject-specific machine and deep learning regression models were developed. For the first time in the state-of-the-art, our work emphasizes on dynamic tasks rather than static tasks, where we frame the fatigue estimation as a regression problem rather than a classification problem. Our pHRI system is mainly composed of a collaborative robot driven by an admittance controller, a force sensor for measuring the human force, and two EMG sensors attached to the user's arm for measuring the muscle activation during the pHRI tasks. The acquired EMG signals are either processed to extract features for machine learning models or transformed to the time-frequency domain for deep learning to estimate the fraction of cycles to fatigue, which we call FCF. Training experiments were conducted with 10 participants who interacted with the collaborative robot, driven by an admittance controller, performing lateral cyclic movements of the end effector until the onset of muscular fatigue. Participants completed 3 trials under 2 different admittance damping conditions. In each trial, human force, the end effector position of the robot, and surface EMG signals from the lateral and posterior deltoid muscles were measured. In this investigational study, random forest, XGBoost, and linear regression models were trained to estimate the fraction of cycles to fatigue using 3 frequency domain EMG features and a single time domain EMG feature. The performances of ML models were benchmarked against a CNN-based model. The results demonstrate that the average root mean square error of FCF estimation across participants was around 20%. To examine cross-task generalization of the proposed approach, additional experiments were performed with 1 participant who executed vertical and circular repetitive movements. Models trained solely on the lateral movement data were directly tested on these unseen tasks. In the vertical movement task, EMG signals were acquired from the anterior and posterior deltoid muscles, while the circular movement task utilized EMG signals from the same muscle pair used in the primary dataset. The cross-motion test results indicate that the proposed ML and DL models are robust to variations in movement direction, arm kinematics, and muscle recruitment patterns.